This is Mr. G, and after this video, we should be able to factor polynomials with the difference of squares. Before we can actually talk about how we perform factoring with the difference of squares, we need to take a few minutes and talk about, all right, how do we even recognize when we're allowed to use it? Because difference of squares isn't that difficult to do, but if we try and use this factoring when we're not allowed to, we're going to get an answer that doesn't make any sense at all. So the first thing we're going to do is name the first 15 perfect squares. So I want you to pause the video right here and try and come up with, okay, what are the first 15 perfect squares we know? So we're going to go over the answers in 3, 2, 1. Here they go. So we've got 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. The reason it's important to know this list is one of the things we're going to have to recognize before we can use difference of squares is whether or not we have perfect squares in our polynomials. So that's why it was worthwhile to go over this list. Now let's take a look at sort of our checklist for what we need to see before we can use the difference of squares. So the first thing we need to see, the polynomial has to have two terms. It needs to be a binomial. And basically, the checklist pretty much is the title. It needs to be the difference of squares. Remember, the word difference means subtraction, and squares just means perfect squares. So we need to be subtracting two perfect squares. So that's where the binomial comes in, and we see that we need subtraction in between our two terms. And any number we have, whether it's there or in front of the x or whatever it is, it must be a perfect square. Whether it's a coefficient or a constant, it must be a perfect square. Now, any variables we have, whatever powers that variable has, it must be an even power. So it could be 2, 4, 6, 8, etc. These are the things we need to look for before we can use the difference of squares. Right. So now let's take a look at how it works. So let's say we had x squared minus 25. Well, it checks all the boxes. It's a binomial. We've got subtraction, we've got a perfect square, and the power of x is even. So we're going to rewrite this as the product of two binomials. The first term in each of them is going to be x, which makes sense because x times x would give us the x squared in front of our polynomial, and the second term will both be 5s. And then we just have to make one positive and one negative. Doesn't matter which one. You could have written it as x minus 5 times x plus 5. And that's it. That's it. Now, this 5 came from the square root of 25. Because remember, we want it to be 5 times 5 to get us back to that 25 we saw in the original. So that's how difference of squares works. But why does it work? So here we have a factored form. And again, I think I had them in the opposite order before, but it doesn't make a difference. Whether you put the plus or the minus first, it doesn't matter. So why does this work? Well, for this to work, we need to be able to distribute and get back to our original. But I mean, usually when we multiply two binomials, we end up with a trinomial. We end up with 3 terms. But now I'm claiming that when we multiply these two binomials, we're going to get to just another binomial. Let's see, why does that work? So let's distribute here. X times x is x squared. X times 5 is plus 5x. Negative 5 times x is negative 5x. And negative 5 times positive 5 is negative 25. Now, if you're paying attention and thinking ahead, hopefully you see what's going to happen. It's like, oh, we've got a plus 5x and a minus 5x. They're going to cancel out. So that middle term, or I don't want to say this, what would have been the middle term in the trinomial goes away. And we just end up with x squared minus 25. That's only because we had, let me erase this. That middle term goes away because we have this, I was going to say the same number, but opposite is a better way to say it. We have the opposite term in that second half. So the minus 5 and the plus 5, the same number with the different signs, that's what makes that middle term cancel out. And instead of getting a trinomial, we get a binomial. Right? So that's how difference of squares works. What we're going to do next is example 1. We're going to take a look at each of these polynomials and think, okay, can we factor the expressions with the difference of squares? And if we can, then we're going to factor them. So it might be worthwhile to pause the video right here and sort of try these problems on your own. Think, okay, so for each one of these, run through the checklist. Is it different than squares? And if it is, try your best to factor them. Then, when you've got your answers, come back and check. So 3, 2, 1, let's go over it together. So first up, we've got x to the 10th minus 36. Well, 2 terms. We've got subtraction, perfect square of 36, and an even power of 10. Yeah, we can simplify this, or excuse me, we can factor this with the difference of squares. So it's not just going to be an x in front because it's an x to the 10th. So it's got to be an x to the 5th power. because x to the fifth times x to the fifth would get us back to that x to the 10th power. And then the square root of 36 is 6, so we put minus 6 and plus 6. Okay, it doesn't matter which one gets the plus and which one gets the minus. There we go, fully factored. Now let's take a look at the second one, x squared plus 1. Now, this one is not going to be difference of squares because we see an addition right there. Even though it checks every other box, it's two terms. We've got an even power. 1 is a perfect square. As soon as we see the plus, we cannot do it. We cannot factor it. And some students were like, well, why not? Why not? Couldn't we just do x plus 1 times x plus 1? Wouldn't that work? But it would not, because remember, since we don't have opposites there, where the middle term isn't going to cancel out. That's going to give us a trinomial, not a binomial. So, if you see a plus there, can't factor. Can't factor, at least not with difference of squares. Maybe there's a GCF or something like that, but not in this case. Okay, let's move on to the next one. So 81 times x to the third minus 1. This one is also not going to be difference of squares. It checks a lot of the boxes, but it's missing the even power right there. We've got an x to the third power. I mean, I guess we could try and factor that with like an x to the 1.5 or something like that. Eventually, we might get good enough where, I don't want to say this, not get good enough. Eventually, there might be a problem where that's advantageous, but right now, I would say that's as factored as it can get. Let's leave it just like that. That's not difference of squares. All right, moving right along. Now we've got 49x squared minus 25y to the fourth. This one is difference of squares. It checks all the boxes. It's a binomial. All the powers are even. We see subtraction, and both coefficients are perfect squares. So let's see. The square root of 49 is 7. It's x squared, so it's just going to be x. And so that's going to be 7x in front of both binomials. And in the back, well, we know it's going to be 1 plus and 1 minus. The square root of 25 is 5. And I'm running out of space, of course. Oh, that actually works. Where was I? So square root of 25 is 5, and y to the fourth becomes y squared. And that's going to be minus 5y squared. And there we go. We just factored difference of squares. We're all done with that one. Now let's take a look at 3x squared minus 363. It would be very tempting to look at this and say, oh, we don't have perfect squares, so no, we can't factor this with difference of squares. But we actually can. The first thing you should always look for in factoring is a GCF. Always look for a GCF first. And here, we can divide both of these by 3. So that would become 3 times, let's see, the 3x squared becomes x squared, minus 363 becomes 121 when we divide by 3. And now we've got an x squared minus 121, which we can factor with the difference of squares. So 3 times, and we have to bring that GCF of 3 over into our answer, becomes x minus 11 and x plus 11. So even though we didn't have perfect squares at the start, by factoring out, by dividing out a GCF, we ended up with perfect squares, and we could use the difference of squares. All right, last one for this slide. 2 times 225x to the 8th plus 4 times y to the 22nd. Well, okay, we've got a GCF in front, but that's not going to affect anything. That doesn't matter. 225 and 4s are both perfect squares. We've got even powers, but we've seen addition. As soon as we see addition, it's like, oh, no, not perfect squares, and we move on with our lives. All right. Hopefully that made sense. Let's jump to example 2 now. Now that we've got sort of our a good foundation of recognizing difference of squares, let's look at a couple problems that are a little bit more challenging. So we got to factor the expression negative 1 over 81a to the 10th plus 16b squared. All right, the first thing that worries me is that plus right in the middle. We know that if there's addition, we can use difference of squares, but we have a minus in front here, which we have not seen yet. Now, whenever I'm factoring, I personally don't like minuses in front, so whenever I have a lead coefficient that's negative, I divide by a GCF. Now, it's probably tempting to look at this and say, well, there is no GCF. There's nothing in common there, but I'm going to divide by a negative 1. I'm going to divide by a negative 1. So our answer is going to be negative times something. We don't know what's in the parentheses yet, but we'll get there in a second. So it's going to be negative 1 in front, or just negative times 1 over 81a to the 10th minus 16b squared. So now that plus in front, once we divided out a negative 1, became a negative. Now we can use difference of squares. And some of you might be saying, but wait a minute, that 1 over 81, is that a perfect square? Yeah. A fraction is a perfect square if the numerator and the denominator are both perfect squares. And that's what we see there. 1's a perfect square, 81's a perfect square. So we can use difference of squares now. Let me see. So that's going to be 1 over 9. Just take the square root of the numerator and denominator. A to the fifth. Then it's going to be minus 4b. And then we write the same thing. Let's see if I have enough space here. So that's 1 over 9, a to the fifth, plus 4b. Did I say write the same thing? I guess it's the same thing with a different sign. Everything's the same with the sign. And we're done. We just factored it. Last one for this video. All right, so we dealt with one with fractions. Now we're going to deal with one with decimals. We got to factor the expression 1.21 m to the fifth minus 0.36 m to the third. Okay, I mean, it's two terms. I see a negative, but we've got odd powers here, which makes me a little worried. Remember, whenever it says factor, the first thing you should look for is a GCF, and these two terms have something in common. We can divide, let me slide this over so I have a little bit more space for my answer. We can divide both of these by an m to the third power. So when m to the third power goes in front, it's going to be m cubed times something. Let's show the rest of our work down here. So n to the third times 1.21 m squared minus 0.36. Yeah, because the m to the thirds just cancel out there, so we just get 0.36. Now we just have to factor this binomial if we can, and we can, because now it's difference of squares. Don't get thrown off by these decimals. 1.21, that's still a perfect square, or I guess it's not a perfect square because it's a decimal, but we can sort of treat it like it's a perfect square. This is just going to be 1.1 squared, because 1.1 times itself would get us back to 1.21. So that's going to be 1.1 m minus the square root of 0.36. That would just be 0.6. Yeah, 0.6. I have to double check myself in my head. And then we write it with an addition. So 1.1 m plus 0.6. So that was a quick lesson on difference of squares, going over how we can recognize when we can use difference of squares, and then how difference of squares can sort of look a little bit more complicated, throwing some fractions, some different signs, some decimals at you. Hopefully this all made sense. As always, if you have questions, let me know. Enjoy the rest of your day.